Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the spectroscope, UV spectroscopy. What is the reason of UV spectroscopy? Then we have discussed about the spectrophotometer, working of that spectrophotometer, and then after that we have discussed about how the Beer's-Lambert's law is applicable and how it is worked there. And after that we have now today what we are going to discuss. Let's see over here, types of electronic transition. Whatever the important question may appear in the exam, so that we have also on this topic mainly, one, why glass does not use for making the sample container. Second one, absolute ethanol is not used in UV spectrophotometer. The reason we know that. And now describe the types of electronic transition. So how do we define the electronic transition? What are the type of the electronic transition, and which organic molecule will show which type of electronic transition? So with the help of suitable example or with the proper diagram, we will study this. And we know that there are three types of electrons are present. Number one, sigma electrons are present in sigma bond. Second one, pi electrons present in a pi bond. And third one, non-electron present in the non. So there is when the ultraviolet molecule when ultraviolet radiation strike the organic molecule, the electronic excitation takes place, means the ground electronic excitation, the electron moves into the higher energy state, from ground energy state to the higher energy state. Generally there is a transition. How the transition allowed, there are number of possible transitions but out of that, according to the selection rule, only allowed transition we are going to study here. Let's see here. Generally with the help of diagram, let me draw the diagram over here. Just the electronic transition figure indicate as a electronic transition. Here we can call it as a sigma electron, and as we know that this is a bonding molecular orbital, the electrons are present, and in the anti-bonding molecular orbital the electrons are present sigma star and the pi star. These star, the distinction between bonding electron and anti-bonding electrons are represented by or marked by such kind of asterisk. Remember, this is called as a anti-bonding. And now this is a figure indicate that electronic transition that is shown over here. This is a sigma electron, and that sigma electron generally Here let me draw this transition only here, sigma, and then next one here is a sigma star, you can call it, and there is a non-bonding electron. Suppose here is a non-bonding, we can call it, and here is a pi electron, and here again is a pi star. This is a electronic transition. Now the allowed transition, when ultraviolet strike to the molecule, the transition occur from sigma to sigma star. This is one of the allowed transition, sigma to sigma star. First one is called as a sigma to sigma star transition. Sigma to sigma star transition. Now what type of the organic molecule shows this transition? Let's see here. And as we know that the absorption of electromagnetic radiation by organic molecule in the UV and visible region involve promotion of electrons sigma pi n from ground state to higher energy state sigma star and pi star. Figure shows all possible electronic excitation that occur in organic molecules. The wavelength of absorption depend upon the energy difference, that is delta E is equal to, here delta E is equal to nothing but delta E2 minus delta E1, and the relation between wavelength and energy is E is equal to Sc upon lambda. E is equal to Sc upon lambda. This is the relationship as we know that while studying introduction to spectroscopy. From this relation it is clear that smaller the energy required for excitation of electron, larger is the wavelength of absorption. The value of delta E depends upon molecular structure, and hence indirectly the value of lambda max is also depend on the molecular structure. And thus by studying the ultraviolet spectrum lambda max, we can deduce the structure of unknown compound. The relative energies for transition are in the following order. So here sigma to sigma star, then pi to pi star, then non-bonding to sigma star and non-bonding to pi star. These are the four allowed transition which is shown in the diagram. These are the possible. Now look at the energy order of this. The relative energies for transition are in the order relative energies. The relative energies are energy order is found to be sigma to sigma star, which is higher than pi to pi star, then n to sigma star, and then n to pi star. This is a general, here make the correction over here. Here n to sigma star, sigma to sigma star, n to sigma star, and here pi to pi star. Here the larger one, then second one is this one, and third one this, and fourth one is the last one. So this is a relative energy order. The types of electronic excitation, from figure we see that there are four major types of electronic excitation taking place in the molecule. First one is a sigma to sigma star transition. Let's see here. In this type of transition, the promotion of electron from bonding sigma orbital to anti-bonding sigma star orbital takes place. As we know that electron from sigma bond are tightly held, and hence sigma to sigma star transition is a high energy process and absorption takes place at very short wavelength near about 150 nanometer. Example belong to this class are saturated hydrocarbons like methane, ethane and other paraffins. As absorption is beyond the range of ordinary spectrophotometer and not recorded in UV spectrum, therefore N-hexane can be used as solvent for UV spectroscopy. Figure 5.5 illustrate sigma to sigma star transition. And as we know that this sigma to sigma star transition is shown like this. This is a sigma bond formation. Now the sigma to sigma star transition, this one sigma to sigma transition, and there will be such type of this one, and here is a this one. This is a sigma star transition takes place, and this is nothing. This figure indicate as sigma to sigma star transition. And the example of this type is a methane, as we know that CH-4, or maybe as a ethane. Ethane means CH3, or some other molecule N-butane, or maybe as a N-pentane or N-hexane. This type of the compound. 1, 2, 3, 4, 5, 6, 7 heptane, or maybe as a hexane. So that type of the organic compound generally shows this type of the transition, sigma to sigma star transition. Now let us move on to the next point. The next point which we are going to discuss over here, the second one, that is a N to sigma star transition or pi to pi star transition. Let us see the pi to pi star transition. Here sigma to sigma star transition, let me show here only, and what type of the molecule example we will see over here. Now let's see second one. Second one is a second type will be pi to pi star transition. Pi to pi star transition. What type of the organic molecule can show pi to pi star transition, that we will see over here. In this type of transition, the promotion of electron from bonding pi orbital to anti-bonding pi orbital takes place. Compound having multiple bonds undergo pi to pi star transition. For example, alkene, alkyne, carbonyl compounds, nitriles and aromatic compounds. Alkenes, ethylene generally absorbed in the region 170 to 205 nanometer and is in the far UV region. However, molecule containing two or more conjugated double bond absorb above 200 nanometer near UV region and figure 5.6 illustrate the pi to pi star transition. Let us look at over here. There is a carbon double bond over here we can show. Now as we know that this is a pi orbital, generally here 4, 1, 2, 3 and 4, that is a side wise overlapping over there. And now when they shows as a pi to pi star transition, the orbital becomes like this. Here the orbital, anti-bonding orbital looks like this here. So this will be the anti-bonding orbital. This is a pi to pi star transition. And what type of the compound shows? Alkene or the aromatic compound, like as a containing as a carbon-carbon double bond. This type of the molecule can show, because there is a sigma bond, along with that sigma bond there is a pi bond, and therefore along with that sigma to sigma star transition, predominantly there will be a pi star transition. So now third transition will be the N2 sigma star transition. Let's see third type of the transition over here. Third type, which is N2 sigma star transition. N2 sigma star transition. So what type of the organic molecule can show? What type of the organic molecule will show N2 sigma type of the transition that we are going to see over here? In this type of transition, the promotion of electron from non-bonding orbital to higher energy anti-bonding sigma star orbital take place. Compounds containing non-bonding or unshared electron present on heteroatom such as oxygen, nitrogen, sulfur and halogen etc. undergo N2 sigma star transition. Alcohols, amines, ethyl alkyl halides, thiols undergo this type of transition, and these transitions are less energetic and hence occur at longer wavelength. N2 sigma star transition can be represented in the figure which is shown over here. Now the organic molecules such as alcohol, let us see over here, then it can show N2 sigma star transition. Sorry, here show the N2 sigma star transition, and now here CS3O, then H, one electron over there. So that type of the transition, the epsilon value for this transition are very small, hence absorption is very weak. Therefore, from the point of view of structure determination, N2 sigma star transition has less importance. Now last one is the N2 pi star transition. What type of the organic molecule? Generally the organic molecule like as a alcohol which has ROH, amines RNH2, halides RX, or the thiols RSH. Means the saturated compound containing as a heteroatom, that type of the organic compound exhibit N2 sigma star transition. There is a sigma to sigma star transition always there. In addition to that, there is a non-bonding electron to the anti-bonding sigma electron over there, and therefore this is the third type of N2 sigma star transition. Now moving toward the next type, that is the fourth one, which is N2. Fourth one is this one, N2 pi star transition. N2 pi star transition. So now here N2 pi star transition, what type of the organic molecule exhibit or shows this type of the transition? In this type of transition, the promotion of electron from non-bonding orbital to higher energy antibonding pi star orbital takes place. Compound containing double bonds involving heteroatom, double bond involving heteroatom, carbon oxygen double bond, carbon sulfur double bond, carbon nitrogen double bond, nitrogen oxygen double bond undergo N2 pi star transition. The N2 pi star transition, the N2 pi star requires minimum energy, which in turn shows absorption toward longer wavelength. And here, out of 4 types of electronic transition, we are mostly concerned with N2 pi star and pi 2 pi star transition, which are less energetic and absorption occur in the UV region. The relative energies are in the following order: sigma to sigma star, just now we have seen sigma to sigma star, N2 pi star, pi to pi star, and what we can call it as that is, and this N2 sigma star transition generally occur in the molecule like acetone. Let us see here, CH3. There is a carbon oxygen double bond, the lone pair which is present over there, and it can show N2 pi star transition. So here you will see CH3, C double bond O, there is a this type of the transition occur, and the wavelength, it can show both the type of the transition, pi to pi star transition also, and which is also shown by this compound here, CH3, then C double bond O, then CH3, but the wavelength are the different in this case. Transition is a weak, transition is a strong. Pi to pi star transition is a, here is a strong, and this will be the weak transition. And now, but in this particular case, it absorb at 280 nanometer and it absorb at 190 nanometer. It will absorb at 190 nanometer and it will absorb at 280 nanometer. That is a wavelength. They are exactly opposite to the, what we can call it as a opposite to the energy. Energy and the wavelength are inversely proportional to each other, and therefore this is there. Now significance of epsilon or the molar absorptivity. The epsilon values indicate the probability of the excitation of electron. Higher epsilon values indicate the probability of excitation of electron is high. The peak of acetone at longer wavelength, that is 280 nanometer, has epsilon only as a 15. This peak is due to N2 pi star excitation. This shows that probability of this excitation is low. The peak at shorter wavelength, that is 190 nanometer, has epsilon is 100. This peak is due to N2 pi star transition excitation and has high probability. In general, all N2 pi star excitation takes place at higher wavelength, low energy, but has a lower probability of excitation. On the other hand, pi 2 pi star transition require lower wavelength, higher energy, but their probability is high. Epsilon values are also affected by solvent polarity. Polar solvent increases epsilon value for pi 2 pi star transition, whereas non-polar solvent increase epsilon value for N2 pi star transition. Consider these are the example we have seen. Now moving toward as a very important point, what we can call it as a terms used in UV spectroscopy. So let us see here one by one what are the important terms used in UV spectroscopy. Number one is terms used in UV spectroscopy. That is a point of discussion. Terms used in UV spectroscopy. Terms used in UV spectroscopy, that is the point we are discussing over here. Following terms are frequently used in UV spectroscopy. Number one is a chromophore. Chromophore. How do we define as a chromophore? One more question always appear in the exam. So remember, how do we define chromophore and what are the example of chromophores? Listen carefully. Chromophore means what? It is isolated functional group capable of absorbing UV radiation, which means a scientist name he called such type of the group is a chromophore. Listen once again. Chromophore, it is a isolated functional group capable of absorbing UV radiation, is known as chromophore. And the examples of that chromophores, now let us see. Examples are here. We know that NO2 or C triple bond N, or maybe C double bond N, C double bond O, or C double bond C, or C double bond S, etc. These are the compound. These are the carbon-carbon double bond, carbon-oxygen double bond, carbon-nitrogen double bond. All are the group are responsible. They can absorb as a UV radiation. If they are in a isolated form also, they can absorb as a UV radiation, and therefore according to as a definition, once again you remember, chromophore, it is a isolated functional group capable of absorbing UV radiation, is known as chromophores, and these are the example of chromophores. Now let us move on to the next important terms used in UV spectroscopy, that is called as a axochrome. This is called as a axochrome. Axochromes. Now axochrome, it is a functional group. It is also as a functional group which itself, it is a functional group which itself does not absorb UV radiation, but when it is attached to a chromophore, shift the absorption to longer wavelength some of the oxochromes are OH. The examples are OH, OCS3, NH2, etc. These are the example of oxochromes. What do you mean by the oxochrome, or how do you define as the oxochrome? As oxochrome, it is a functional group which does not absorb UV radiation, but when it attached to chromophore, shift the absorption to longer wavelength is known as oxochrome. And the examples are OH, OCS3, NH2. This type of the functional group, they do not absorb UV radiation. But when they attach to the chromophore, let's see, we know that benzene is an example of chromophore, right? This is a chromophore because it containing carbon-carbon double bond, and carbon-carbon double bonds are alternatively placed, and therefore it is act as a chromophore when it attached to, suppose as a phenol OH. As we know that benzene itself it shows a lambda max. The characteristic of lambda max found to be 255 nanometer, and this is known as a chromophore, right? Chromophore. When the hydroxyl group OH attached to that chromophore, that phenol has lambda max is a greater than, is nearly is a 260, we can call it. This is called as oxochrome. This is called as oxochrome. So lambda max is found to be is a 260 nanometer. If suppose we have another example, OCS3, toluene. This is a oxochrome. This is nothing but as a oxochrome. We can show over here, and the lambda max is found to be is a 270 nanometer or 265 nanometer. So these are the example of some of the terms, and remaining terms we will see. I think that we will see in the next lecture. Let us stop today here. Thank you. Have a nice day.